So, we are on to lecture 2 or the second lecture, and we are solving problems on metallurgical thermodynamics. Basically, as I have indicated, we are we will be performing mostly equilibrium calculation, determining composition of slag, melt, etc. in equilibrium with appropriate phases. So, yesterday I discussed one problem, and in that we wanted to calculate the gas partial pressure, mostly the CO2 ratio, which is in equilibrium with FeFeO at 1200 Kelvin, 1 atmosphere total pressure. Before I start discussing the problem which I was discussing yesterday towards the end of the lecture, that is dissolution of diatomic gases, and posing a problem on that, I would like to make one correction. I think towards the end of the lecture, I very hurriedly actually I have shown this to be K equilibrium, and I found out that this value of K equilibrium is equal to 0.53. Up to this point, everything was perfect, but then without performing the calculations, I straightforward wrote it that this is what it is, and which is actually not true. It should be other way around. So, this is a mistake I have done in yesterday's lecture. So, rest of the discussion stays good. So, only thing is that this is an error. So, those of you who would be referring to the lecture, you must have noticed yourself, or you can make that correction. So, the fate of the system with respect to a gas composition containing 70% carbon that I was discussing towards the end of my the problem I was solving on this iron oxide reduction holds good, because 70% is greater than 66%. So, whatever I said holds good. So, with these statements, I now go on to discuss the second problem which I pose to you. So, dissolution of diatomic gases. So, let us formulate a problem. Okay? And so, we have a system here, and because it is not desirable to write the problem in words, so you can formulate the exact wordings of the problem that I am posing here yourself. Otherwise, it will take quite a bit of time in just writing the problem on the board itself. So, and most of the examples that I am going to cite would have reference to iron and steel making because of my own personal bias, because I am too involved. So, whatever example comes to my mind often in terms of chemical thermodynamics, in terms of kinetics, in terms of heat transfer, they all tend to close down towards or approach towards systems concerning iron as well as steel. So, let us say we have a steel melt here, okay, and this steel melt is subjected to a nitrogen atmosphere, and let us say that the system is at 1600 degrees centigrade or 1873 Kelvin. And yesterday I was showing you that if it is a pure nitrogen atmosphere, the reported value of equilibrium melt composition at 1600 degrees centigrade is somewhere around 457 to 476. So, this means that because these are experimentally determined values, so none of the two investigators get the same values. So, this essentially indicates that a steel melt subjected to a pure nitrogen atmosphere and Pt is equal to 1 atmosphere, okay, will have somewhere around 457 ppm, and this is wet percentage actually, and the conversion of wet percentage to ppm. So, simply take the wet percentage value multiplied by 10 to the power 4 and you get the parts per million concentration. So, the steel melt is subjected to a nitrogen atmosphere, and let us say that this is given to be partial pressure. So, now it is I made it that it is exposed to So, atmosphere. So, therefore, and suppose the steel melt is, let me complicate the problem a little bit, it is an alloy steel, it contains carbon which is equal to say 0.4%, and these are all weight percentage, even though I may not be explicitly saying, and let us say that this is chromium is about 0.6 weight percentage and manganese is about 0.6 weight percentage. This is the alloy steel composition, and that is what it is. And we want to calculate that if partial pressure, if such a melt at 1600 degrees centigrade is exposed to atmospheric air, where nitrogen concentration is 0.79 or 79% nitrogen is there. So, what is the equilibrium nitrogen content? That is the task, and all these things are given to us. Total pressure is equal to Pt, and I will say that the reaction which governs the process, that is half N2, which I had written yesterday. And for this reaction, of course, to perform thermodynamic calculations, we will either be given you the delta G naught value as a function of temperature, or we can provide you directly the value of the equilibrium constant for the reaction. I would like to draw your attention, many a time equilibrium constant values will be given, okay? Not for the forward reaction, but for the backward reaction. Okay? So, with respect to not the forward reaction, but with respect to the backward reaction. So, therefore, the reaction may be the equilibrium constant, the reaction will be written like this. Okay? It can be written something like nitrogen is equal to half N2, and so there is inverse relationship between the two, as you can see. So, you have to figure out that for which reaction the equilibrium constant is given, whether it is for this reaction or whether it is for this reaction. So, that is just to give you a tip. Okay? So, let us say that the equilibrium constant, yesterday we have shown that if delta G naught values is given as a function of temperature, you can easily calculate the equilibrium constant by invoking that formula delta G naught is equal to minus RT ln K equilibrium. So, let us say that the equilibrium constant is given to you, and equilibrium constant for this reaction is basically given as log K equilibrium, which also is represented as log K sub n, okay, and that is given to be 2.937 minus 518. So, either yesterday's problem we have considered that the delta G naught value is given, now directly the equilibrium constant value is given to you, and this is divided by T. So, if you take T is equal to 1873, okay, you can find out that log K equilibrium will come out to be 2.66, or K equilibrium will come out to be 457. And this you must understand that this value which is following is valid when nitrogen concentration is expressed in ppm and this is the gas pressure is in atmosphere. So, that is when, so that is the condition in which, because these are all experimentally determined values, based on how the concentration was measured. So, when nitrogen is in ppm and atmosphere, and that is the way value which it comes out to be this. Now, if we write down the equilibrium constant for this reaction, okay, and then we see that the equilibrium constant will come out to be K equilibrium will come out to be the Henryan activity, because it is a dilute solution case. So, we would say this, okay, and then square root of partial pressure of nitrogen, and this is, we know, is given is equal to 0.79, and Hn we can write out is equal to Fn, the interaction activity coefficient multiplied by weight percentage of nitrogen, okay. And then if you do this, then I can consider because I have considered it wet percentage, I could have written Fn into nitrogen concentration in ppm, and that is equal to 0.457, but that wet percentage and ppm are related. So, I will say this is equal to not 457, but it is equal to 0.457, because I have not written ppm, I have written in wet percentage scale itself. Okay. So, if I consider that I want to convert this wet percentage of nitrogen, then I will multiply, I will convert into ppm, then I multiply both sides, and then this concentration becomes ppm. Now, so therefore, we have an equation, a final equation comes out to be Fn, the activity coefficient multiplied by wet percentage nitrogen is equal to 0.0457 into square root of 0.8. Now, Fn needs to be calculated. So, you have to know little bit of thermodynamics here, that Fn, log Fn is typically given in terms of summation of interaction parameters multiplied by the wet percentage of the alloying elements. So, this could be written as E carbon nitrogen into wet percentage nitrogen carbon plus E carbon, and this is now chromium nitrogen into wet percentage chromium, and then plus E manganese nitrogen into wet percentage nitrogen. And also we can write E and N, which is known as the self interaction coefficient or self interaction parameter. Typically these values, as you all know, are given values. So, these are all known values and they are tabulated in thermodynamics. And for example, we have given the composition. So, composition is known to us, the interaction parameters are given to us. The interaction parameters, for example, this is 0.11, this is equal to minus 182, 0.182, and this is equal to minus 0.091, and interaction self interaction parameter is equal to 0. So, therefore, log Fn value can be easily calculated from given the composition, and therefore, I can say that if I multiply all these values, you can note that these values are, this is positive, this is negative. It depends, it tells you that what is the role of the alloying elements by looking at the sign. I mean, this thermodynamics should be clear to you. You look at the sign of the interaction parameter, so you can say immediately that chromium is a strong carbide forming element. Okay? So, a nitrate forming element, nitrogen in presence of chromium, lot of nitrogen is going to go into steel. In presence of manganese, lot of nitrogen is going to steel, and these have great ramification in steel making, for example. So, therefore, if you substitute these values, therefore, 11 multiplied by wet percentage of carbon, which is 0.4 minus 0.182 into manganese. So, this is 0.6 plus minus 0.091 multiplied by, and this is also 0.6. So, if you do this, the value comes out to be, log of n will come out to be minus 1.198 if you do the calculation. Okay? And then therefore, the Fn value will come out to be 0.063. So, if you now go here, so we can see that I have written, so this will give me that the weight percentage of nitrogen in equilibrium, okay, what percent of nitrogen in steel in equilibrium with atmospheric air at pressure is equal to, total pressure is equal to 1 atmosphere and temperature is equal to 1600 degree centigrade is basically 0.0457 divided by 0.063 multiplied by square root of 0.063. So, therefore, you can see that this is this value. So, this is basically square root when you do square root. So, it is 0.063 I think, yes, and this is 0.0457. So, you can calculate very easily. So, this is roughly approximately is equal to 0.9 into 0.045 or 457 divided by 0.063. And this value, as you can see here, that is going to come out to be substantially larger than this is what? This is the value we have gotten at 457 ppm of nitrogen. If you remember, this is the value of equilibrium nitrogen content at 1 atmosphere pressure in pure iron, okay, where there is no alloying elements. And now you can imagine if you this value, this parameter, this is the role of the pressure as well as the reduction in pressure has reduced the value, but introduction of the alloying element has increased the weight percentage of nitrogen. So, this could be almost, if we look at the value, 15 times more, and the value should come out to be something like 0.6812. That means 6,800 or 0.68 weight percentage. So, you can imagine that these alloying elements, what they have caused, they have increased the solubility of nitrogen considerably in steel, and the steel now contains about this much of nitrogen. So, you can compare the values at 1 atmosphere pressure vis-a-vis pure iron melt vis-a-vis a alloy steel melt, and then calculate for yourself that it is. So, you can understand now. So, as I said that once you solve the problems, you should be able to extract. It is not just merely getting the number is enough. So, you must understand that what is the implication of this problem. This gives us several messages. For example, it tells us that if you tap an alloy steel from a furnace which will pass through the ambient atmosphere and fall into a ladle, the chances of nitrogen pickup from the atmosphere is going to be significantly larger than it is in the case of plain carbon steel, because of the enhanced equilibrium solubility of nitrogen in alloy steel contents. So, the alloy steels will tend to dissolve much nitrogen. Okay? So, therefore, this essentially will tell us that an alloy steel containing chromium and manganese will require extensive amount of degassing operation in order to drive out, and there may be various if you for example introduce titanium, okay, in that case what happens is titanium is again a strong nitrate forming element, the solubility would further increase. So, after you solve every problem, I would say that one thing we should practice, that you should box the answer always. Okay? This is one good practice, and we say that. So, this is the answer of the problem, okay? And that you should make a habit of boxing your answer all the time. And also, after solving the problem, you should be able to do this exercise yourself. Try to draw 2 or 3 inferences from the problem, and then you will see, you could see many things which otherwise you were not able to understand, not able to see. The numbers allow us to visualize. I say 2 persons are taller. Okay? How tall? It is only when I say one is 4 feet 3 inches and another is 6 feet 5 inches, then only you can visualize, oh, it is a substantially, one person is substantially taller than the other person, because you have the numbers. Generating the number is very, very important. So, once you generate these numbers, it allows you to visualize the process or the calculation of the results much more meaningfully. In this context, many times we could solve the problem analytically, okay? And I will show you a case. For example, suppose in this case, hypothetical case I am considering, that suppose the self interaction parameter of nitrogen, which I consider to be 0, is not 0. You will find out in many cases not always self interaction parameters are 0. In that case, what happens is that we have, this is Fn, as we have seen, the value of Fn comes out to be, when self interaction parameter is 0, the value of Fn has come out to be this, that I have already shown to you. Now, you imagine that if Fn is not is equal to 0, a hypothetical case, in that case what happens is you can say that this is a known side, let us put it like this for making. So, B is a known parameter. So, I would say that Fn, so Fn will come out to be now log Fn is equal to, I will say alpha, all is a known term which is this particular term, plus interaction parameter, so self interaction parameter of nitrogen to nitrogen, and this is equal to beta into weight percentage nitrogen. So, this is the self interaction parameter of nitrogen, and log of n formula would come out to be like this. So, we have one term, second term, third term, and the fourth term is this. First and second and third term culminates to this parameter which is constant, which is equal to 0.063, and the self interaction parameter beta value is known. So, alpha and beta are known, Fn value has come out to be this. Now, if you take logarithm of this, then you see log of Fn plus log of weight percentage nitrogen is equal to log of this parameter, which is again is equal to B prime. Now, if you put log of Fn is equal to this, then what you get an equation something like weight percentage nitrogen plus some parameter, I would say alpha prime, and then this is log weight percentage nitrogen, and then this is equal to some other constant which is beta prime. Because I cannot put a value of beta, the self interaction parameter, which is 0, I am just telling you that those problems where you will find that the self interaction, the parameter for which you want to determine the concentration, the self interaction coefficient is non-zero. In that case, what is the problem that you are going to face? That is what I am trying to elucidate here, rather than we can solve it, we can see that in the context of another problem. But if you look at in this particular case, if self interaction parameter of nitrogen would not have been 0, in that case the final equation that I would have gotten is of the form x plus k log x is equal to some parameter where k is a constant, numerical value is there, beta 0 is constant, and this sort of an equation also you encounter in thermodynamic calculations dealing with composition determination, and this you cannot solve by analytical means, you have to solve it by trial and error. Now, if you want to solve it by trial and error, where from you want to start? You want to start from weight percentage of nitrogen value, because you have one idea that look, I know the equilibrium value in the case of iron, pure iron, which is 457. So, my first value, so if you do a trial and error, you put not 457, maybe 490. So, the base value from which you start is a known value, because you will not do a trial and error by putting a value of 1 or 10 or 100. You have to have some idea about a tangible value for x, which is the weight percentage of the allowing elements or the species under consideration, and that is known from some other calculation we have performed. And in this case of nitrogen, I would have said my initial guess value of weight percent would be somewhere close to 0.0457 or something like that, and that would have from that I could have seen that whether I should increase the value or decrease the value and how much, and then eventually we can by increasing the value gradually we should be able to find out that what is constant. So, you require numerical method to solve this kind of an equation, which we call as a transcendental equation. Okay, x plus log x is equal to k, and therefore not always you will be able to solve the equations resultant expressions analytically. Be prepared for that. Okay, so try for yourself. We will pose a next problem, and there possibly we can see that if we want to find out that how the self interaction parameter can be accommodated into the calculation scheme. So, this is about the gas dissolution, dissolution of diatomic gases. We now want to address a third problem, which is also quite popular in, and this is a commonality, but this is a thermodynamic calculations basically, and this one can put it under iron and steel making also, and this is deoxidation thermodynamics. I want to show you a calculation or a numerical. Deoxidation thermodynamics. What is the problem? Let us formulate the problem. So, again we have steel melt, for example. Let us say this is a 100-ton steel melt. This steel contains initially, after steel making, initial oxygen, and this oxygen is dissolved oxygen, and that is equal to 500 ppm. Temperature is 1600 degrees centigrade. Every time we put this temperature, because that is the general steel making temperature, it could have been something else. Okay. And then we are adding, suppose, aluminum, which is known as one of the powerful deoxidizer element. So, we want to, our target is from oxygen initial, dissolved oxygen initial, which is 500, we want to go to final oxygen, final, okay, which is say 40 ppm. Aluminum is a very powerful deoxidizer. So, we can get up to 10 ppm, 8 ppm final level of oxygen. And then we want to find out that, look, under ideal condition, if you want to reduce oxygen from 500 to 40 ppm in the bath, how much of total aluminum needs to be added to the bath. Now, there are two different components of it. One we call as a thermodynamic requirement, that with this final oxygen there will be some amount of aluminum dissolved in the melt. So, initially aluminum may be 0, suppose, and once we start adding aluminum, what happens? Aluminum dissolves into steel, and then in steel dissolved oxygen which is present reacts and forms a new phase, which is Al2O3. Now, Al2O3 can be a pure Al2O3. The problem can be of different level of complexity, or Al2O3 maybe if you are doing complex deoxidation, aluminum, silicon, manganese, okay, then you can have, you know, a silico-manganese aluminosilicate inclusions, or you know, you can have a silicate inclusions containing both aluminum and Al2O3 as well as MnO. So, complex deoxidation products can also form. Okay. So, therefore, depending on the deoxidation process, but this is a I pose the problem at a very simple level. I am saying that the moment you add aluminum is a pure aluminum as solid forms. Okay. So, the deoxidation product is pure alumina, which need not be the case always. If it is pure alumina, we understand that activity of Al2O3 is going to be equal to 1. If it is in some kind of a mixture, aluminosilicate or a mixture of oxides, say MnO as well as Al2O3 as well as SiO2, in that case we have to know the activity of alumina in that particular deoxidation product. So, if in the later case, if you want to find out the activity of Al2O3 in that particular deoxidation product, we have to be given two things. One is the deoxidation product composition. This is to be given. How much it is? 45% Al2O3, 30% SiO2 and so on and so forth. So, that composition it is to be given, and we have to have composition, activity composition diagrams available to us. You may have seen ternary diagrams, binary diagrams, etc. So, these two informations are to be provided. activity composition diagrams, relevant activity composition diagrams. These are two. Based on these two information, no matter what is the system or what is the deoxidation product, we will be able to find out, because all these calculations will require that the activity of the deoxidation product or the product forming must be known. And as I said, that in the pure case it is simple, but here it is not so simple. But given this two, it is very easy for us to find out that what is the activity from the given composition of the deoxidation product. So if we assume that this is at equilibrium, so we can say that K equilibrium is equal to activity of Al2O3, and then we will say that it is Henryan activity. These are all dilute solutions, parts per pp, and then activity of oxygen raised to the power 3. And basically, as we have seen, that we can write it like this: Henryan activity coefficient FAL square into weight percentage aluminum squared, Henryan activity oxygen cubed into weight percentage oxygen cube. That is the final expression. And as I have indicated, that this equilibrium constant will be given to us either in terms of the delta G naught value, standard free energy change, or it can be given directly as an expression in terms of the temperature. Okay? And let us see that what is the value. The log K equilibrium for this particular case is given as minus 20.57 plus 64,000 divided by T, and if we substitute this T is equal to 1873, in that case what we find out that this is equal to 13.6, okay, and therefore this should come out to be plus 13.6. So, therefore, K equilibrium is equal to 10 to the power 13. Very large value of equilibrium constant essentially indicates that the product is very, very stable indeed. So, that is reflected. Alumina is a very stable product, and it is clearly reflected from the value of the equilibrium constant. So, now let us make an assumption. First assumption we are making that this is activity of Al2O3 is a pure phase. As I said, I posed the problem, and let us say that the Henryan this is also is equal to 1, because I have told you if they are not is equal to 1, okay, in that case you have to calculate the activity coefficient, activity of aluminum, activity coefficient of aluminum, this is equal to 1 and this is also is equal to 1, to make my life simple. So, this will be given to you, it will be said that you can calculate the total aluminum requirement as accurately as possible. In that case, we will not ignore this, we will consider, because we have seen in the previous problem that what is the role of this activity coefficients, it can really jack up the composition. Of course, to be able to calculate this, the interaction parameters will be supplied to you, the composition of the melt will be supplied to you, and then you should be able to calculate that F aluminum and FO without any problem. But if you consider the self interaction parameters also, then you should be prepared. Okay? So, at least I would say that if by neglecting the self interaction parameters and considering FAL and F0, you can get a reasonably accurate value of the deoxidation calculations. Okay? And as I said, that if you consider the self interaction parameter also, then eventually what it needs it, you will not be able to solve it analytically, you have to make a table, do trial and error, and then determine the value itself. So, therefore, under these assumptions, we will say that we can write down that what percentage aluminum square is equal to, this comes out to be 10 to the power 13.6, okay. And then we have what percentage of oxygen cubed, so that is equal to 0. This is, that is what it is, and this is going to be equal to 1, because 40 ppm, what is the aluminum we are calculating? With this aluminum in equilibrium with 40 ppm of oxygen in the bath. And if you now do these calculations, so 10 to the power minus 13.6, and then this is 10 to the power 9, so multiplied by 10 to the power 9, and this is 64, and this comes out to be 10 to the power minus 4.6 by 64, and this gives us a value, what percentage of aluminum is equal to square root of this. So, this is equal to 10 to the power minus 2.3 divided by 8, that is the value, and this value comes out to be now approximately a very small value, or 7 ppm only. You can see that the aluminum which has gone into melt, it has displaced 40 ppm oxygen, but at the expense of that, 7 ppm aluminum has gone, and this value, had it been a manganese deoxidation, would have been substantially larger, and this value is very small, and this, the smaller is the value, this indicates that powerful is the deoxidizing agent. So, this is equal to 7 ppm. So, now having calculated, so this is the thermodynamic component. Okay. Now, we go to the calculation of the total aluminum deoxidation requirement, aluminum deoxidizer requirement, total deoxidizer requirement. So, one requirement is, you could have imagined that if I would not have taken f Al is equal to 1, here I would have encountered x plus log x is equal to k kind of an equation here. Okay? I would not have been able to determine the value of what percentage aluminum so easily. It is because I have ignored the self interaction parameter, and that is why I could get the value, and this point you must remember by heart. Okay? So, therefore, what is the thermodynamic requirement? Now, first thing is how much of oxygen is there in the melt. We have 500 ppm. So, oxygen present, oxygen initial is 500 ppm. So, 0.00, 500 ppm 0.05, and 100 kg is this much. So, in 100 tons, okay, this is the amount in kg, and that is equal to, we have 50 kg of oxygen is present in the bath. Number 2, oxygen final, and that is equal to 0.004 by 100 multiplied by 100, 100 and multiplied by 1000. This is the kg to ton conversion, and this is equal to 4 kg. So, therefore, delta O, the amount of oxygen which has been removed, is 50 minus 4, which is equal to 46 kg. So, one component is that aluminum has gone into steel to stay in equilibrium, which is 7 ppm, and the other component is the aluminum is sitting in Al2O3, okay? And then you can find out that how much of, for this much of oxygen, how much of aluminum is needed, because you can say that 54 grams of aluminum needs 48 grams of oxygen. Okay? So, therefore, we can say that 46 kg of into 48, 46 by 48. So, this much of aluminum has actually gone and is sitting as in Al2O3, and this comes out to be something like 52 kg. This part is we call as the stoichiometric requirement of the deoxidizer. Okay? So, stoichiometric requirement. And now we calculate the thermodynamic requirement. So, 7 ppm. So, this is how much? So, this was the value weight percentage. So, 100 multiplied by 100 multiplied by 1000, and that gives me only 0.7 kg. So, most of the aluminum that I have added is sitting in the deoxidation product, or it forms a major forms essentially the stoichiometric component of the system. And in this case, therefore, you can say that this is A, thermodynamic requirement, and this is B, the stoichiometric requirement. The total aluminum requirement is going to be 52. This is not exactly 52, but I have approximately indicated plus 0.7, that is equal to 52.7 kg. You can also find out, so in the deoxidation product we have 52 kg of aluminum is sitting, and there we have 46 kg of oxygen has eliminated, which has gone into the deoxidation product. So, 52 plus 52 plus 46, that gives you the total deoxidation products that is formed. So, that may also be a part of the problems asked, that calculate the total amount of deoxidation product. So, I will simply add the amount of oxygen removed with the amount of stoichiometric requirement of the deoxidizer, sum them up, and then say that the total deoxidation product formed is equal to 52 plus 46, and that is equal to 98 kg. So, you should be able to perform these calculations with various permutations and combinations, and as I have indicated that had the deoxidation product been something else, suppose I have a system where I say that it is a calcium aluminate deoxidation product, okay? And then I could say that, look, you give me now the phase diagram, okay, and or activity versus composition diagram, which will show me for what percentage. So, I will first give you number 1 the deoxidation product composition, that I will say that, look, the deoxidation product is calcium aluminate, which is in 55 weight percentage calcium oxide, 45 weight percentage alumina. This is I have given. Now, you have an activity versus composition. So, from that given composition, you can find out from the given diagram that what is the corresponding activity of Si alumina, what is the corresponding activity of CaO, and that activity which you determine from the activity composition diagram needs to be substituted in Al2O3. Okay? So, similarly, if you use for same thing applies in manganese silicomanganese deoxidation, for example, okay, which you call as a complex deoxidation. There also you will see that you will have a equilibrium, you will have a activity composition diagram given, where active as a function of the composition of the deoxidation product, okay, the various activities of the two different phases will be mentioned, and that diagram is to be used and substituted and used and applied in the deoxidation calculation, particularly when you apply use the activity of the constituents which form the deoxidation product itself. So, we will continue our discussion, and I think I want to show you one more type of calculations in thermodynamics, and then we will move on to the next topic.